You guys had a good Wednesday? Did anybody show up? Nobody showed up, right, for class? Awesome. It's not going to be normal to miss class. I don't like to miss class that early on, especially because it just sort of sets a bad precedent, he's saying. And I don't foresee any other meetings. I know for this particular thing, we're not going to have any more meetings that'll affect you guys. We have some on Thursday, but that doesn't affect anybody as far as I'm concerned. But anyway, just so you know, we might have one other missed class. All right, but I'm sorry for that. Let's see, we are having an exam soon. Just want to remind you so that you have it on your horizon. If you look at your syllabus, I think it might be in the front of your workbook too, I'm not sure. But the exam schedule is right here. Our next exam is on the 14th of September right here. So we're at, what, the 2nd? So we have 2 more days next week and then 1 more day. So it's going to cover, of course, all of chapters 1 and 2. It might cover a portion of chapter 3. But it's not that far away, this next exam. So make sure that you've mastered chapter 1 and that you've begun on chapter 2. I have posted the concept test for chapter 1, so if you go there, you can download it by clicking on chapter 1. If you want, you can, oh, never mind. Yeah, so you can download those. Morning, guys. John and Alex? No, Matt. Okay. So anyway, just make sure that you're on top of these things. Work through the homework for chapter 1. Begin working through the homework on chapter 2. Test, test. All right, good. Let's get started. So we left off last time. We were looking at average velocity and how to find average velocity for position versus time graphs. Let's look at one. We were looking previously at one that was linear, and we're going to do it very similarly if we have a graph that's nonlinear, except we're not really going to be finding the slope of the graph. We're going to be finding the slope of the line between 2 points. So you can just think of it as you're really just pulling the data off of the graph. And Elena, I realize I didn't bring your calculator. Do you need it during class? Okay, y'all just wait 15 seconds, okay? I'll be right back. Nobody leave. Be right back. Awesome, you're all still here. Will you pass that back to Elena? All right. So if we have something like this, and you will have a graph on the test that you'll have to analyze in various ways, and we're going to do it quite a bit. Let's say this graph, I want to know the average velocity from 0 to 10 seconds. So this is my point at 0 seconds. This is my point at 10 seconds. We can think of this, hey Tyler, we can think of this as just pulling the data from the graph. So remember, average velocity is delta x over delta t. My x final is 30, x initial is 20. So in the numerator, I'm going to have 30 minus 20. And then in the denominator, I'm going to have my t final, which is 10 seconds, minus my t initial, going from 10, 0. This is in meters, this is in seconds. So this works out to be 10 over 10, or 1 meter per second. That is my average velocity. You can also think of this as I'm finding the slope between this point and this point. And it turns out that that part of the graph is pretty linear, so it's the slope of the function at that point too. That's described by the line. We can look at different points. Say we're going from 10 to 30 seconds on this graph. So this is my initial point right here. This is my final point right here. And I'm going to connect a line between those two. If I'm finding the average velocity, I can think of taking the final position, which is minus 20, the initial position, which is 30. So that would be minus 20, that's my final position, minus 30 divided by 30 seconds minus 10 seconds. And that gives me minus 50 over 20 or minus 2.5 meters per second. Now, as I said, I just sort of did that by pulling the data off the graph for the particular points, but that's also going to be the slope of this line will equal minus 2.5. And you can probably see that, we were finding the slope, right? Y final minus Y initial, X final minus X initial, rise over run. It comes out negative because velocity is what type of quantity? Is it a scalar or a vector quantity? This value for average velocity is negative. Does that mean that it's a scalar or a vector quantity? Have we talked about this? It's a vector quantity. And vectors just means that it has direction, right? And so negative would mean that it's either what or what in a one-dimensional. What's negative? Left or down, right? Okay? So our negative denotes either left or downward motion. All right. That's average velocity. That's sort of important, but mainly we're going towards looking at instantaneous velocity. And instantaneous velocity is the velocity at a particular time. That is an instant. We'll talk about this in terms of a derivative soon. Um, I don't know if this is different from my notes. I'm sorry. A what, and I give the blank of the instantaneous velocity. We're just going to skip that line, okay, folks? It's not that important, obviously. But we're going to define the instantaneous velocity in this way. So let's say that I have a position versus time graph, like this one, and I can find the average velocity. This is the average velocity. It's that delta x over delta t at a particular time, or rather over a particular time interval. And what we're going to do with this is we're going to say the average velocity is over a particular time interval. We're going to take that time interval and we're going to collapse it down to just a particular instant. So what this is saying, it's the limit as delta t approaches 0. That means that we're letting delta t, our time interval, it might have been 20 seconds before. We're going to take it and we're going to let it get really, really small. We're going to let it approach 0. And that means that we're no longer looking at a time interval, but we're looking at a particular instant in time. So this is taking the average velocity over a time interval and collapsing it down to a particular instance in time. And of course, this is, as we said before, this is the definition of a derivative. And so our velocity, our instantaneous velocity, will be the first derivative of the position function, dx dt. And we'll work through some problems like that. You're certainly going to see a problem like that where I give you a function and you have to tell me what is the function for the velocity and for the acceleration. We'll work through one of those soon. So in a nonlinear graph, the derivative is just a fancy word for what? For a graph or for a function. The slope of a function. So if I have a representation of that function drawn on a coordinate system, the slope of that function is the derivative. So the slope of the function, but actually the slope of a tangent line, hey Grace, the tangent line is equal to the instantaneous velocity. So let's say I want to know what is the instantaneous velocity at this particular instance in time. Then I would need to find what is the slope of that function at that particular time. Now the slope changes, right? Over here the slope is small, over here the slope is big. So the slope at this particular place is going to be somewhere in between. And the way we're going to do this is we'll draw what's called a tangent line. There is a mathematical definition for a tangent line, but we don't really need to worry about it. It has to do with each individual point is some equal distance from the function. But I like to think of it as sort of balancing on that function. So say, for example, we had a function that looked like this, like a half circle, then the tangent line at this point would be what type of line? Would it be vertical, horizontal, somewhere in between? It would be a horizontal line. It's like it's a board balancing on an old guy's belly, okay? Or like a seesaw. And then that is our tangent line. Whereas at other points, say over here, my tangent line will look like that. So as you go through these, and we'll do one in class, you'll be able to sort of get a feel for how to draw the tangent line. And you'll have some latitude in what answer you get for the slope of that line because it's not going to be exact and not everybody's going to have the same answer. All right? But the slope of the tangent line will give us the instantaneous velocity. Let's look at this problem, and y'all can try it on your own. I want to know what is the instantaneous velocity at t equal 4 seconds. T equal 4 seconds right there. I'm going to zoom out just a little bit. You can see the whole graph. The instantaneous velocity at t equal 4 seconds. Notice there are some options that you can just get rid of right away. So you might want to think about what those are. We'll go about 10 more seconds. So stopping at 1:30. Remember, you can ask your neighbor what they put if you like. Actually, though, before we do so, just want to remind you that there are a couple of answers here that cannot be correct. And a lot of you have those answers right now. So look at this. There are two of these answers that are not possible with this. I want to know what is the tangent line at this point, and think about, of these, which two are not possible. They're just not possible answers, and so you can just eliminate them completely. So just think just a second more. Ask your neighbor if you want. All right, I'm going to stop at 208. 208. Okay, which of the two answers, or which one of the two answers is not possible? What's the first one that's not possible? D is not possible, right, because my tangent line at that function is going to have a positive slope, a rising slope, and D would be the opposite. There's another one, too, that's not possible, and which is that? E is also not possible, because to have a slope of 0 would mean I'd have a horizontal line. So let's see, it's either A or B. It's a little tricky in how you do this. Um, and in fact, this one is a little more of a judgment call than you would have on the test, but there is a correct answer for this one. And it has to do with how you draw your tangent line. Let's see, our tangent line, I'm going to go from right about there to, say, right about there. So my tangent line at this point is going to look like that. My tangent line of that function will look like that. And then I want to know what is the rise over run. My rise is here, the vertical. Um, that rise is going to be 6. And what is my run? What do you, some of you say 2 and some of you say 4. Yeah, look closely at the graph and tell me what you think. Uh, the change in time is, what is my initial time for this particular function or this particular tangent line, and what is my final time? Y'all making a very common mistake, those of you that are saying one of those numbers and then the other one is correct. Okay, what do y'all think? It is 2. Why is it not 4? Or rather, let me ask you another question. Why did you say it was 4? And it's okay here to say that it's 4, but not on the test. Why did you say it was 4? The box is right. Did you do that? It's okay. Yeah. Yeah. So be careful. On a graph, whenever you're looking at a graph, you never count the boxes. You always look at the axes. So we're going from 3 to 5 here, and my run goes from, or rather my rise goes from -3 to 3. So it's going to be 6 divided by 2, which is going to be 3 meters per second. So that is my instantaneous velocity at that point. Uh, so to be 1.5, just to show you, to be 1.5 would mean I would have a run of, gosh, it would sort of look something like this. And that's not the tangent line for that particular function. Okay? All right, so A is the right answer, right? Or is it B? Yeah, A is the right answer. Good job, y'all. In the previous graph, what is the average velocity between t equals 0 and 2 seconds? I'm going to write the options up here. I know not quite everybody has their workbook yet. -1. What is it between t equals 0 and 2? The average velocity. Between t equals 0 and 2. What is the average velocity? Oh, ask your neighbor. Okay. Morning. All right. We'll stop at 110. 110. We're sort of a little bit all over the board. So many of you have the right answer. All right, good. B is right here. Going from t equals 0 to 2, just like we did before. We're going from t equals 0 to t equals 2. Now, you should know right off, looking at this, you should say, oh, the answer has to be what? Positive or negative? Negative. That doesn't really help you since all the options are negative, but often in a multiple choice question, you'll have some that are positive. So here, between 0 and 2, I do x final minus x initial. That's -4 minus -1 divided by t final minus t initial. That's 2 minus 0 meters over seconds. That's -3 over 2, which is -1.5. See, what was the next favorite answer? A? Not sure what you did there. I'm not sure why y'all put A. But what is that? Read a 2 as a 1. This 2 right here? Oh, okay. But the answer is -1.5. Okay, folks, you'll certainly have some questions like that. Y'all good on that, perhaps? I mean, about 2/3 of you are good on it, but there's some practice in the homework. And if you look back at the old test, you'll find problems like this on every exam. A problem where I give you some function, and I ask you to calculate something about the motion of that function. We're going to do it some more because we're going to look at some other types of graphs and estimate their derivatives and their integrals and what have you. Okay, so now let's look at acceleration. Remember, we're talking about three different things when we're talking about kinematics. Do y'all recall the three things? D, V, and A. What was D? Displacement, or we call that delta x. V was velocity, and now acceleration. So acceleration is sort of like the third thing in that quiver, and it describes how the velocity changes with time. And just as we dealt with how the position changed with time and velocity, we're going to do basically the same thing here. And the same definitions will fall out as well. So our average acceleration is going to be delta v over delta t. This is how our velocity changes over a particular interval. So for example, if the initial velocity is 10 meters per second, that's going to be VI, and the final velocity is 20 meters per second, that's VF, then we can calculate our average acceleration. It would be 20 minus 10 divided by 2 minus 0, and that's 10 over 2, or 5 meters per second squared. Those are the units for acceleration, meters per second squared. We had meters per second over seconds, so that's meters per second squared. Meters over seconds times seconds. You can also think of this is how the meters per second change over a given time interval. So it's meters per second per second. So like for example, this one would be going uh, 0 meters per second, say at t equals 0. How fast would it be going after 1 second? It would be going 5 meters per second. And then after 2 seconds, it would be going, you get 5 meters per second for every second. So after 2 seconds, it would be going at what speed? 10. After 3 seconds, 15, 20, 25. Every second, it will increase by 5 meters per second. Okay, it's a little rule. Students are often confused by this. So if velocity and acceleration are in the same direction, the speed increases. However, if velocity and acceleration are in opposite directions, then the speed decreases. And we can think about this in terms of vectors. So if I draw my velocity vector in this direction and my acceleration vector in this direction, we'll get into vectors in chapter 3, and that'll probably be on the test as well. But the length of this vector determines the magnitude of the vector. It's a graphical way of drawing vectors, and the length will represent the magnitude of the vector. After a particular time, in this case, as time passes, then our velocity vector is going to get bigger because it's accelerating. The velocity and the acceleration are in the same direction. However, if my velocity and my acceleration are in opposite directions, say that my velocity is in this direction, but my acceleration is in this direction, then after a certain amount of time, my velocity is going to decrease. It's going to get smaller. And we can see that like if we throw something up in the air. As I'm going up in the air, my velocity is in what direction? Up or down? As the pin, if I throw it up in the air and it comes back down, as it's going up, the velocity is what? Positive or negative? It's moving upwards. That's positive. But the acceleration is in which direction? You might not know this right off, but it is negative though. The acceleration in free fall problems is always down. That's why when we drop something, it always goes down. It never goes up. But when I do throw the thing up, it has a velocity that's up, an acceleration that's down. And is it slowing down or speeding up as it goes up? It's slowing down. That's because the velocity and the acceleration are in opposite directions. But after it reaches the top and starts coming down, is it slowing down or speeding up? Speeding up. So acceleration then can be positive even when the object is slowing, and it can be negative even when the object is speeding up. And this example is like something in free fall. Because if I have something and I drop it, it has a velocity that increases, but it has an acceleration that is negative. So it has a negative acceleration, but it's speeding up. The point of this is, and students are sometimes confused, I don't think that y'all will be, but students are sometimes confused that negative acceleration does not mean slowing down. No reason for that to mean slowing down. Sometimes you can have negative acceleration and it will be slowing down, like this case, as it goes up to the top. But sometimes you have negative acceleration, that means it's speeding up, like this scenario. Okay? Okay, good. All right, so let's just sort of go through this, what is the average acceleration of this? Did we just do one like this? Huh? No? Yes? Okay, so V initial, V final, I'm going to have minus 20 minus negative 10 divided by 2 minus 0. This is meters per second over seconds. So this becomes a positive. And I get negative 10 over 2, which is negative 5 meters per second squared. Right, is this object speeding up or slowing down? Look at the initial and final velocities and tell me, is it speeding up or slowing down? It's speeding up. It went from minus 10, that is 10 meters per second to the left, to minus 20, that is 20 meters per second to the left, or maybe down or to the left. So it is speeding up, but it has a negative acceleration. So this car has a negative acceleration, but it is actually speeding up. I want you to take a moment to sketch the velocity versus time graph for that scenario. So think about, what is my initial, what is my final velocity, and then I want you to sketch the velocity versus time graph for that scenario. This is the origin, this is 0, 0. Time equals 0, velocity equals 0. Go ahead and sketch what you think the velocity versus time graph will look like. You'll have lab on this next week. It will be on the exam. You'll have to sketch velocity or position versus time graphs for different scenarios. All right. What kind of slope does this line have? Does it have a positive or a negative slope? It has a negative slope. In fact, we'll see that the slope of a v versus t graph, that is the derivative of velocity with respect to time, is going to give us the acceleration. And we'll see that when we define instantaneous acceleration. And so we know, since it has a negative acceleration, this line should have a negative slope. Which quadrant is it in? Is it in the first or the fourth quadrant? It's in the fourth quadrant, right. So it is going to be a straight line. It's going to start, somewhere like here, and it'll go like that. My initial velocity was negative 10. My final velocity was negative 20. This was 0. This was, what was the time? 2 seconds. So our graph is going to look like that. You'll have some more complicated graphs for your exam, and we'll do some examples of them. But this is a good start. We're only going to consider particles that have constant acceleration. That means that that v versus t graph will always be a straight line as far as we're concerned. There are some cases where you have changing acceleration in the world, but there's also a whole heck of a lot of things that have constant acceleration. So we'll just think about that for the purpose of this course. All right, need to define instantaneous acceleration. It's going to be the same argument as what we had before. So our instantaneous acceleration is going to be the limit as delta t approaches 0 of what, do you think? The limit of what value as delta t approaches 0? Remember what we did for instantaneous velocity? It was the limit of what value? I remember. Anybody remember? Nobody remembers, do you? What was it? Change in time? Uh, yeah, we are letting our time interval go to 0. We're letting delta t go from big to small to a particular instance in time. But with instantaneous velocity, we took the limit of what function or what value. The what now? The position function with respect to what? Average velocity. That's one part. Thanks, Nicole. So that delta x over delta t, the derivative of that, or excuse me, the limit as delta t approached 0 of delta x over delta t, that was our instantaneous velocity. Remember, because we had average velocity over a big interval, and then we collapsed it down to a particular point. That's called taking the derivative. Here, we're going to take the limit of what, do you think? Not average velocity. I mean, not average, right, we're going to take the limit of our average acceleration, right? Our limit of delta v over delta t. Right, so this is our average acceleration, which is the acceleration over a big time interval, and then we're going to let that collapse down to a particular point in time, a particular instant. And then this is the definition of a derivative, so it's going to be dv dt. The derivative of the velocity function, it's going to be 3t plus 4t squared, some function that describes the velocity with respect to time. And as we've already talked about, the acceleration, or we talked about this with regards to instantaneous velocity, the acceleration is the slope of the tangent line on a graph of velocity versus time. So the velocity is the slope of the tangent line of the position versus time graph. This is the slope of the velocity versus time graph. So say, for example, I know the slope here. Is it going to be positive or negative, the slope of this point? It's going to be negative. And how about here? Positive. Which one is going to have a larger magnitude of slope? Here or here? The first or second? The second one, right. We can draw them, and you should get some practice drawing these because you'll need to for the exam. Uh, that's a good tangent line for that point. You might have a little judgment call on this one, but something like that. This has a negative slope. This has a positive slope. This has a small slope. This has a big slope. Talking about the magnitude of the slope, a small magnitude or a big magnitude. That means that this is accelerating just a little bit, but this is accelerating a lot more. This is accelerating in the negative direction. This is accelerating in the positive direction. And this other one, the slope is positive or negative? It's a positive slope. And is it changing or unchanging? Unchanging. So this is a positive constant acceleration. All right, let's look at a function. Let's say that I have this velocity function. And as we said, let me just sort of jog your memory. The instantaneous velocity is dx dt. The instantaneous acceleration is dv dt. So to be correct, I should draw vectors over x and v. But from here on, I'll probably drop those vectors. And when I just draw x, v, or a, we'll assume that I'm talking about instantaneous position, velocity, or acceleration. Okay? So let's think about this function. This is the function for the position of a particle. We'll see actually when we get into kinematics that a lot of particles follow this type of function because this function describes something that travels with a constant acceleration. So what I want you to do is determine what is the velocity at t equals 3 seconds, and then what is the acceleration at that same time. So go ahead and try that out. It's going to require you to take the derivative of that function. If you've forgotten, uh, ask a neighbor or can look back. I'll just remind you that if I have a function, that's how we do a t to the n, the derivative of this function d dt is going to be n times a times t to the n minus 1. I think we use different values or different variables, but all right. So what is the velocity at t equal 3 seconds? And then what is the acceleration at t equal 3 seconds? All right. What is the derivative of this function? 3 plus 4t. Right, I can imagine that there's a 1 right here. I say 1 times 3, that gives me 3 times t to the 1 minus 1, that's t to the 0, or 1. Anything to the 0th power is 1. And then 2 times 2 is 4, t to the 2 minus 1. And then here, implied is t to the 0. 0 times 4 is 0, so I leave that. And so that gives me then 3 plus 4 times 3, which is 15 meters per second. That's at t equal 3 seconds. And then the acceleration at t equal 3 seconds, what's the derivative of the velocity function? Is just 4. So I have a constant acceleration for this graph. Can we draw a velocity versus time graph for this? Think about what the velocity versus time graph will look like for this particular function. Think about which quadrant it's going to be in, what's going to be the slope of the line. Is the slope going to be increasing or decreasing? Which quadrant is it going to be in, first or fourth? It's going to be in the first quadrant. I know that because the velocity is never negative, right? 3 plus 4t, it's never negative. Is it going to be a positive or negative slope? It's going to be a positive slope. I know from this value, which by the way is the same as this value. This is the equation of a line, right? Y equals m times x plus b. So where's the line going to start? Is it going to start at the origin or somewhere above or below there? Above. How far above? 3 units, right? Because that's the y-intercept. So my velocity versus time graph will look like this. All right. What does the position versus time graph look like? This is a little trickier. So if you remember your geometry, not geometry, algebra, I guess. You probably know it. This is a straight line, constant positive slope. What does the position versus time graph look like? Where does it start? What quadrant does it start in? What quadrant does it stay in? What happens here? Yeah, Frankie, that's very close to right. I have some functions drawn. Love to see them. You have one, Grace? No, it's okay. What quadrant is it going to start in, you think? First or fourth? You think the first, but it's actually the fourth. It starts at t equals 0. My value for this function is what? Negative 4. So I know that at t equals 0, it should be right there at x equal negative 4. And then is it going to go up or down? It's going to go up. Is it going to be a straight line? No. Do y'all know what shape it's going to be? A parabola, right? It's a quadratic function, so it'll look like that. Now let's look at this. Remember, the slope of a position versus time graph gives us what value? I forget. Which is it? The slope of a position versus time graph? Well, oh, you know what we can do? We can just look at the units. because slope, which is rise over run, would be y-axis over x-axis. That's going to be what units for the slope? Jesse, I think you said it, right? What is it? Meters per second is right. So the slope of a position versus time graph is the velocity, okay? So the slope of this graph, oh gosh, it looks like it's increasing, right? Well, look at the velocity. The velocity is also increasing. The slope of this graph is increasing, and that's why this graph is increasing. Also, look at the sign of the slope. The slope here is increasing. It's also what? Always positive, always negative, or does it transition between positive and negative? Let me ask that question as a clicker. Is the slope for this red line, is the slope positive, always positive? Is it always negative? Or is it sort of transitioning between negative and positive? The slope of this line, this function, is it always positive? Is it always negative? Or is it sometimes positive, sometimes negative? Okay, awesome. All right, I'm going to stop at 28. Okay, most of you have this, but let me just make it clear. The slope of this line, it's positive here, it's positive here, and it's positive here. But you're saying, I know why you put negative, because it's in the fourth quadrant, and stuff is negative down in the fourth quadrant, right? But not the slope of this line. It doesn't matter where it is. The slope of this line is always positive. To have a negative slope in this quadrant, it would have to look like this. That would have a negative slope. All right? I don't mean to harp on that, but it's important for what we're going to do next. All right, I want you to describe the motion in these plots. Describe, is the velocity positive or negative? Is it increasing or decreasing? Just answer those two questions right now. Is the velocity positive or negative? And is it increasing or decreasing? I'll give you about 15 seconds to think about it, and then I'll ask you. All right, this first one. Velocity positive or negative? Positive. Why is it positive? Why do you say it's positive? Slope is positive. The slope of a position versus time graph, that gives us velocity. Uh, is it the velocity increasing, decreasing, or staying the same? Right, the position's increasing, but the velocity is staying the same because the slope stays the same. I'll write this down in a second. Let's do this one. Velocity positive or negative? Positive is right. Is the velocity increasing, decreasing, or staying the same? Don't answer right away. Is the velocity increasing, decreasing, or staying the same? And when you ask yourself that question, you ask, what is the slope doing? Is the slope increasing, decreasing, or staying the same? And that will be what the velocity is doing. Now, altogether, the velocity is doing what? Increasing, right? Because the slope is small here, slope is big here. And how about here? Uh, velocity positive, negative, what? Zero. It has zero slope. And it's also not changing. All right, so positive velocity, not changing. That is, the velocity is not changing. Here I have positive velocity, and the velocity is increasing. Here I have velocity equal to 0, and the velocity is not changing. That's what that arrow means, that it's remaining the same. All right, let's ask about acceleration, because on the test I'll give you a position versus time graph, and I'll say, what is the acceleration of this graph, of this particle that's moving? Is it positive, negative, or 0? This one has positive velocity, and the velocity is not changing. Is the acceleration positive, negative, or 0? 0. Because the velocity is not changing, if I have any acceleration, the velocity will be changing. Here I have positive velocity, and the velocity is increasing. Is the acceleration positive, negative, or zero? Think about it for just a second. Think about those two rules. If the velocity and the acceleration are in the same direction, it's speeding up. If the velocity and acceleration are in opposite directions, it's slowing down. And so you want to ask yourself, which of these scenarios is it? And is the acceleration positive, negative, or zero? Which is it? Positive is right. I'll write that down in a second. And here the acceleration is zero. The velocity is not changing. Anytime the velocity is not changing, it's zero. So I have acceleration equal to zero here, acceleration equal to zero here, and here I have a positive acceleration because the velocity is positive, it's speeding up, and so that means that it is positive acceleration. All right, let's try these. Similar thing. Uh, is it velocity positive or negative? Speeding up, slowing down. Acceleration positive or negative? On this one, is the velocity positive or negative? It's positive because the slope is always positive. Is this object speeding up or slowing down? Slowing down because initially the speed is big in the positive direction and then it gets gradually slower in the positive direction. What is the sign of the acceleration for this thing? Positive, negative, or is it zero? It's not zero. Is it positive or negative? Negative. Why would it be negative? Like it's in the first quadrant, the velocity is positive. There's no reason because it's opposite, because it's slowing down. Right. Okay, because this object is slowing down and because this object has positive velocity, that means that it has a negative acceleration. So I have positive velocity. That's given by the slope, like the sine of the slope. I have slowing because the slope is decreasing. And I have uh, negative acceleration. That's this scenario. I throw something up, and then up there it stops. It slows down until it gets to the top. This one, I have a negative velocity here, and I have a positive velocity here. And in all cases, on both of those scenarios, the acceleration is equal to zero, with the exception of right here, where the acceleration is something else. It's not zero. Okay? Goodness, bless you. Okay, these are, notice velocity versus time graphs. On velocity versus time graphs, we'll always have a straight line because we're dealing with constant acceleration problems. In this case, is the velocity increasing or decreasing? Increasing. It's small here, it gets bigger here. Is the velocity positive or negative? Positive. It's positive not because it has a positive slope, but because it's in the what quadrant? First quadrant. These are positive numbers over here. What's the acceleration? Is it positive or negative? It's what? You'd think it'd be zero, wouldn't you, because of what we've been saying? It's velocity versus time, so it's positive acceleration. All right, so remember the slope of a v versus t graph gives us the acceleration. So I have a positive velocity, I have an increasing speed, and I have a positive acceleration. How about this one? Positive or negative velocity? Be careful. Positive or negative velocity? It is constant velocity, but is it positive or negative? It's positive. I know why you'd say zero because the slope is zero, but we're talking about a different set of graphs now. The slope doesn't give you the velocity. The slope now gives you the acceleration. Because remember, rise over run, v over t is acceleration. So this has a positive velocity because it's in the first quadrant. It has a positive value. It also has a constant velocity because that value never changes. And so several of you said the acceleration is 0, right? Because it has 0 slope. So it has a positive velocity. It has an unchanging velocity, or constant, all right, constant. It has acceleration equal to 0, and that's also the slope equals 0. And then here we have something that changes. Here I have acceleration equal to 0, and here I have what acceleration? Positive or negative? Negative acceleration is right, because the slope is negative. All right, we're going to have some more practice on this, so don't sweat it if you're not fully getting it, but it seems like many of you have it. But if you don't, that's okay. We're going to have some more on the concept test when we do those. All right, let's try this one. Which of these plots is impossible? These are all position versus time plots. Which one is impossible? All right, I'll stop at 30. 30. Oh, awesome. Just being able to look at graphs, do you guys realize that that's groundbreaking? Like a couple hundred years ago, people didn't even know what a graph was. They never really thought about looking, plotting, and visualizing data in this way. So, man, you guys are on the cutting edge in the history of the world. I'm not being sarcastic. I'm being serious. That to plot data, and even to take data, is just something that's so far out that people didn't do for so many thousands of years. But you guys, you're like cutting edge scientists. You're awesome. B is right. Why is B not possible? Right, because Jackaroo here was in this position and this position at exactly the same time. Okay? Hey, knock knock. Interrupting pirate. Arg! You don't like that one, do you? Okay. All right. Park is running slowly in gym class, but then he notices Jenna watching him. So as guys tend to do, we tend to do, he speeds up. Which of the graphs could represent his motion? Going slowly first, and then speeds up. Okay. Also, I'm going to stop at 35. I'm a little disappointed because nobody put, there are actually two correct answers here, right? What are the correct answers? C and what else? No, not A, unfortunately. Let's look at why C is right. C is right because here he has a small slope and here he has a big slope. Is it time to go? Sorry, small slope, big slope. And here he has a small slope, big slope. So either C or D would be correct. But since nobody put D, I don't have to deal with it. So we'll just put C as the right answer. But it could be either C or it could be D if he's running in the negative direction. Alrighty. I sent a message out. We're having like a special lunch today. We're gonna do these, I think, monthly. It's sort of like a, I don't know, a discussion of matters of science and faith. And if you guys want to come, we're gonna meet in the conference room right here at noon, right after the 4M class at noon. It's a brown bag thing, so you bring your own lunch. But I sent out an email about it. If you have any questions, just let me know. Have a good day. Have a good weekend.